Okay, now we are in Excel and I have brought here the mathematical computation here. So step number one, we have to look at the minimization cost. So we have to see how many costs that we have. In this problem, we have three costs. We have the transportation cost, we have the fixed facility cost, and we have the variable cost. So you start by implementing this. So I will call here the transportation cost. The other one what we have is the fixed facility, and then the other one is the variable, and sometimes they call it handling fees. I'll just put it here for you. And this means that the total is what we want to minimize. So this will be the sum of all these costs. So this is our minimized Z actually, I would say cost. So what do we do next? So they are saying that the transportation cost is Cij matrix multiplied by Xij matrix. Now, what is the Cij matrix? The Cij matrix is given here. This is what was given, and since I already have it, I will bring it here and paste it here for us. And this is the Cij matrix, and times the Xij matrix. Now the J matrix becomes, that is what we do not know. So we always mark this yellow. Okay. Now, since we already here, can we now first put this demand so that I could have some space here? So what I will say here, I will implement the demand constraint here. So it is the regions. You see these regions, they are the ones which need this demand. So the demand needed in Västerås is given as 92, and the demand given here at Örebro is 90, and the demand given at Stockholm is 250, and the demand in shopping is 81, and the last one is 101. So so it means that what we are, all this data now that we already have, I can now remove this so that I could have more space here. We have the Xij matrix, we have the Cij matrix, and then they are telling us that the first cost is the sum product of Cij matrix times Xij matrix. So we come here and implement it. We say is equal to the sum product of Cij matrix, which is Cij matrix, and then multiplied by, in my case it is semicolon, in your case it could be comma, multiplied by the Xij matrix, close bracket. And then they have told us, remember that we have, for every distance moved per case is 3. So we multiplied all this by 3 and say enter. So now we have implemented the transportation cost. So if you click here, you should be able to see the whole computation. It is the Cij matrix times the Xij matrix times 3. Okay, so we go now to the next one. Now we have plus fixed facility cost. Now the fixed facility cost, it's given per distribution center. So if I just use this here, we are being given that the fixed facility cost is given, and I will pick it from here since we already have it. I hope I don't bring other data with me as last time. So if you paste it here, so, and then we have the y variable. So the y variable, we say that it's a decision variable and it is a set of zeros and one, which means it is in the network or not in the network. It is open or closed. For now, we are looking for only one. And also is that we do not know which one the algorithm will select. So to be secure, we just put this in yellow and we do not know. However, what we know that the sum of this for now, it should be equal to 1. Why? Because we want this whole computation algorithm to select one DC. If we want to, we could put a decision in solver to solve for 2. If we want 3, we put 3 like that. And we will do that for the extended analysis. So we have now the fixed facility cost, we have the Y decision, we have the fixed facility cost, we have the Y decision. So we go ahead and implement it. So it will be the sum product of the F multiplied by open or closed and close the bracket. Mhm. And then the last one, we have the variable cost. So the variable cost is the total of these xij. So the ones that will transport. And what are these xijs? So these xijs is the total sum that will be coming in the production of these distribution centers. So all the sum that is coming from here is what they will charge us 100 per case. So we do that for all the production centers, and then everything that will be here we multiplied by V. So here we have the V cost, the variable cost, and then here we have the X summation of Xij. In fact, you could call it total cases of juices that will produce. And here we are given each one by saying this 100, and I do that for all all these places. And then this total cost is the same as we agreed the total here. So we have to say for all. So if you click here, it should be the same as there. If you check here, it's the same as there. So we have the variable cost multiplied by the total cost that we will incur. So this is the price we will incur. If the total is 70, it is 70 times 100 plus. If we ship 60, it will 60 times 100 plus, like so forth. So we have the variable cost, we have the total of this. Why don't we also insert it in the algorithm? So it will be is equal to the sum product of the variable cost multiplied by the total cases here, and say okay. So if you click here, you should have that, and if you click here, you have all the sum. So now we have all the costs are now inserted. So why don't we put now the subjected to demand constraint? Now the demand constraint in the regions, the ones going, the algorithm will send some demand here, it should be equal to that. So the sum here, the sum of everything going to Västerås, which is our demand region, should be equal. Now you can put here to remember, just should be equal to that. And you do everything, all the demand that will be sent to Stockholm should be exactly equal to the demand there. That's one of the decision constraints that we will put. Now, we have to put the capacity constraint. First is that the capacity constraint, now I will lock it at 1000. We were not given this constraint. If it's not given, you could see here the sum, which is the sum of the demand, 614, yeah, 614, and you could lock it up to 650 or maybe 700, but I want to use this 1000. In your other example, they are using 700, but in here let's use 1000, and then we'll see. So what should we do with this capacity? So we set this capacity for all the distribution centers. Now we want to tell this algorithm that this capacity here that is being produced here should be less or equal to what we can afford. So here it should be less or equal to this capacity. And then immediately we have this idea of excess capacity. Now the excess capacity is as follows: capacity multiplied to check multiplied if it is if that center is this distribution center is a network or not. Then the production, you remove the summation here with this x, the one the cases on that, and then the remainder should be greater or equal to 0. So let's put it in here. So it will be equal to the capacity multiplied by, if it is open or closed, subtract what you will send there, and then the remainder should be greater or equal to 0. This is the decision that we're going to put in solver. So for example, let's say that in shopping the algorithm has decided that it is 1, it is open. Okay, so now it hasn't sent anything and we have excess capacity as 1000. But if it sends 500 to Stockholm, it means the total capacity here that we will pay for 100 each is 5,500. If you remove what the plant could afford, you have excess capacity of 500. If it adds maybe 100 here, it reduces. If it adds another 200 here, it will, but it might continue and say, in order to have minimized cost, we need to send Motion Shopping 500. And then once it does that, we enter into a situation of having negative excess capacity in our plant, and we don't want that to happen. So in order to do that, that's why we implement this excess capacity, and we try to lock it that it can send all the amount, but when we subtract this from the excess capacity, it should be greater or equal to 0. And we do this for all the demand nodes. Now, we have now implemented almost everything. So I will delete this and then we go to solver. So you go to data and then you go to solver. I hope you can see my pop-up. And then solver is going to ask you that you set the objective. So I set the objective as this one here, which is the total minimized Z. And then we want to minimize this by changing the values that we don't know, which is this multiplied by that. So the algorithm will know that these are the changing variables, they are not static. So you click here, you put this multiplied by, in your case it would be comma, in my case it is semicolon, multiplied by these xij's, and then we say okay. Now we have 5 constraints we want to add. So the first constraint that we all know is the demand constraint. So let's add the demand constraint here. We are saying everything going to these demand regions, the white regions, should be exactly equal to what is needed there, which is this. And we say add that. The other decision that we know is the capacity decision, is that everything that is being produced should be less or equal to the capacity. In your case it was 700. We say okay. And then we want this excess capacity to be greater or equal to 0. We don't want it to be less than 0, and we add it. And then the other condition that we know is that this y should be should be a binary. And then we have now 1, 2, 3, 4, 5 decisions, and we make unconstrained variables non-negative, and we solve this using simplex linear programming, and then we hope that we didn't make any mistake, and then we click solve, and then it will think and think, and then it starts to shape something, and then here it goes. It says okay. Now, yeah, so this is the right solution. So sometimes you could enter into these very thin minus things, but you don't have to worry about that. I think you could also make it like in percentage, or maybe, yeah, whatever. But this has it's a really very small number. You don't need to worry about it, and you could make it, yeah. So now we have 202 here, and I think in the lecture you have 202. Yeah, the same thing here. Now the first observation here that we have, the first observation is that in the what you had in the Excel, we have used 2000 capacity, and here in this example I have used 1000 capacity, and here also we used 700 capacity, and we have almost the same. You see, we have minimized also the same. Transportation cost is 12 here, and here it is also 12. Now it means that the algorithm, actually, this is one of the indicators to tell us the algorithm actually is more correct, so that regardless of the capacity dimension, it merges from minimized. For the other condition that we are being told is that all the demand that is going to this region is going to be produced in shopping. So now we go back and see how much was the fixed facility. So we'll be paying 2100 per week. The distance from in shopping is 27, 67, and so forth. You see? Now, the other thing that we can say here is that you could make an extended analysis. First, you could have a scenario analysis whereby we could say that, okay, let's go back to the data and change here and say we had put this to be 1 DC. What if now we change and open actually 2 of them here? So you add that and say, now we are trying to open 2 DCs, and then we solve again. And then it thinks again, and it thinks again, and then it thinks, right. And now it has opened 2. The minimization cost has reduced. Now, what if we say, let's open more of this? So we are going to change, and we have that. And then we solve again. The same data, but we are trying to open now more networks. So we are moving away from centralization to decentralization model. Now it has opened 3. Now you see the amount is not changing a lot, but you have transportation cost, fixed cost, everything here is kind of reducing. Now you could go on and on, and that's what I was trying to show you here. So first you could change this. So we were given here the transportation. So remember, the main learning outcome is this. If you can construct this, that's fine. And the extended analysis, what I wanted to show you is that you could change this distance into hours. So how? You just say that if this cell is l- less or equal to 60, it is indicated by 1 or otherwise 0. And then you do all this for all. So it means that if this is more than 60, it will be 0. If it's less than 1, it's less than 60, it will be 1. And then you're trying to find the average distance. How do you find the average distance? You find the average distance by having the sum product of xij's, you multiply by that distance, and you divide by the demand, the total demand. And then you have the average distance which can be moved for when two DCs are open. And you could also look at that in percentage of with the time dimension. So you do the xij multiplied with per hour divided by the demand, and you can see that you'll be moving almost at 85% within 60 minutes, within